Welcome to AP Statistics. Today we are tackling topic 3.4, justifying a claim based on a confidence interval for a population proportion. In this lesson, we have three main objectives. First, we will learn to interpret a confidence interval in context. Second, we will justify claims using these intervals. And third, we will understand the relationships between sample size, confidence level, and interval width. By the end of this lesson, you will be able to explain exactly what those parentheses and percentages mean, and use them to evaluate real-world claims. Let's start with the most critical part of this topic. How do we actually explain what a confidence interval is telling us? Our goal for this section is to master the standard phrasing used in AP statistics to describe a confidence interval. Recall that a confidence interval is built from a sample proportion called p-hat plus or minus a margin of error. This creates a range of values. The formal interpretation always follows this template. We say, we are C% confident that the interval from A to B captures the true population proportion of, and then we describe the population and the variable in context. Notice we use the word captures. We don't say there is a 95% chance the population proportion is in there. The population proportion is a fixed number. It's either in the interval or it isn't. Adding context is where students often lose points. You must specify who the population is and what success looks like in your study. For instance, look at this interpretation. It includes the confidence level, the interval limits, and a specific description of the population. Now, let's address a common point of confusion: the difference between interpreting the interval and interpreting the confidence level. Our goal here is to explain what 95% confidence actually means in the long run. The confidence level is not about one specific interval. It's about the process. Imagine we took hundreds of random samples of the same size from the same population. For every sample, we calculate a new 95% confidence interval. Because each sample is slightly different due to sampling variability, the intervals will be in slightly different places. Some of those intervals will miss the true population proportion entirely. So, the interpretation of the level is, if we repeat this sampling process many times, approximately 95% of the intervals we construct will successfully capture the true population parameter. Always use the word approximately or about. We can't guarantee exactly 95% because of the nature of random chance. To recap, when you interpret the interval, you talk about the specific numbers you found. When you interpret the level, you talk about what happens if you redo the study over and over. Let's put this into practice with a worked example. This will help you see how to apply these interpretations in a real AP-style scenario. Our goal is to correctly interpret both the interval and the level for a specific study. A school administrator wants to know the proportion of students who support a new dress code. A random sample of 100 students is taken. A 90% confidence interval for the proportion of all students who support the dress code is calculated to be 0.42 to 0.54. In this case, our sample proportion was likely 0.48, and after calculating the margin of error, we got this range from 42% to 54%. First, the interval interpretation. Notice how I included the confidence level, the specific boundaries, and the specific population, all students at this school. Now, the level. I'm not talking about the 0.42 or 0.54 here. I'm talking about the reliability of the 90% method itself. Take a moment to think about this. If majority means more than 50%, does this interval support that claim? Looking at the interval, we see that it contains values like 0.43 and 0.48, which are not a majority, but it also contains 0.52 and 0.53. Because the interval includes values both below and above 0.50, we cannot claim a majority with 90% confidence. We will dive deeper into this justification logic in the next scene. This brings us to a major skill in AP statistics, using a confidence interval to justify a claim. Our goal is to determine if a specific value is a plausible value for the population proportion based on our interval. In statistics, we use the word plausible to describe any value that falls inside our confidence interval. If a value is outside the interval, we have convincing evidence that the true proportion is likely not that value. Let's look at a scenario. A city council claims that more than 60% of residents favor a new park. A 95% confidence interval is calculated as 0.62 to 0.74. Since the entire interval is above 0.60, every plausible value in our range supports the council's claim. Because the entire 95% confidence interval, 0.62 to 0.74, is above 0.60, there is convincing evidence that the true proportion of residents who favor the park is greater than 60%. Now, what if our interval was 0.58 to 0.70? In this case, 0.60 is inside the interval. This means 0.59 is a plausible value. Because the interval contains values less than or equal to 0.60, we do not have convincing evidence for the claim. Remember, if the value you are testing is inside the interval, it is a plausible value for the parameter, so you cannot rule it out. To support a claim that p is greater than k, the entire interval must be above k. To support a claim that p is not equal to k must be outside the interval. Now, let's look at the relationships between our variables. How do the choices we make, like our confidence level or sample size, affect the actual width of the interval? Our goal is to understand how the precision of our estimate changes when we change our study design. Recall the anatomy of an interval. The part after the plus-minus is the margin of error. To change the width of the interval, we have to change the margin of error. First, let's talk about the confidence level. Suppose you want to be more sure that you capture the true proportion. As you increase the confidence level, say from 95% to 99%, the critical value, or z-star, must increase to cover more area under the normal curve. Think of it like a net. If you want to be more confident that you'll catch a fish, you need a wider net. However, a wider interval is less precise. That is the trade-off. Now, what if we keep the confidence level the same, but increase our sample size, n? Look at the formula for standard error. Since n is in the denominator, increasing n makes the standard error smaller. A larger sample gives us more information and less variability. This results in a narrower, more precise interval. To get the best of both worlds, high confidence and high precision, you need a much larger sample size. Let's dig deeper into the relationship between sample size and the width of the interval. This is a very common type of multiple choice question on the AP exam. Our goal is to see exactly how much we need to change the sample size to achieve a specific reduction in our margin of error. Notice the square root in the standard error formula. This means the relationship is not linear. If you want to cut your margin of error in half, you cannot just double your sample size. Let's look at the math. To get a 2 in the denominator of the result, we would need to multiply n by 4 because the square root of 4 is 2. So, to cut the width of your confidence interval in half while keeping everything else the same, you actually need a sample size that is 4 times larger. Let's solve this. The researcher wants to go from 4% to 1%. That is a reduction to 1/4 of the original width. Since we need to reduce the width by a factor of 4, we must increase the sample size by a factor of 4 squared. So, they would need a sample size 16 times larger than the original one. Increasing n improves precision, but with diminishing returns due to the square root. This is why large-scale polls often stop around 1,000 or 2,000 people. To get significantly more precision, they would have to pay for a massive increase in sample size that usually is not cost-effective. Let's wrap up with one final, comprehensive example that brings together all the skills we've discussed. A local news station conducts a poll to see if more than 50% of voters support a new tax. From a random sample of 400 voters, they calculate a 95% confidence interval of 0.47 to 0.55. Our first task is to interpret this interval in context. We are 95% confident that the interval from 0.47 to 0.55 captures the true proportion of all local voters who support the new tax. Next, let's use this to evaluate the station's claim. Does this interval provide convincing evidence that a majority, meaning more than 50%, support the tax? Look closely at the interval. It includes values like 0.48 and 0.49. Since 0.50 is inside the range of plausible values, we do not have convincing evidence that the true proportion is strictly greater than 0.50. No, the claim is not supported, because 0.50 is contained within the interval 0.47 to 0.55, making it a plausible value for the population proportion. Now, a design question. If the station wanted to decrease the width of this interval to make their estimate more precise, what are 2 ways they could do that? They could decrease the confidence level, which would decrease the critical value z-star, making the net smaller. Or, they could increase the sample size. If they wanted to cut the width of this interval in half, they would need to quadruple their sample size from 400 to 1,600. Let's recap what we've learned about confidence intervals. Intervals provide plausible values. Confidence level is the long-run success rate. Use the entire interval to justify claims. Width depends on z-star and the square root of n. You've now covered all the essential knowledge for topic 3.4. You can interpret intervals, justify claims, and manipulate the factors that determine an interval's width. Great job!